Monoidal categories and their representations, Lecture 4, Coherence and Rigidity. Let us recall MacLane's stratification theorem, which we considered on the previous lecture. Theorem: every monoidal category is monoidally equivalent to a strict monoidal category. This means the following. For any monoidal category C, there exists a strict monoidal category C tilde and the monoidal equivalence phi from C to C tilde. In the proof of this theorem, we constructed the category C tilde as the category of all endofunctors of C which commute in a certain precise sense with tensoring on the right with any object of the category C. Now we will use this theorem to establish a property of monoidal categories which is called coherence. So let us describe the setup and the formulation of the problem. Let C be a monoidal category. Let x1, x2, and so on xn be objects in C, not necessarily distinct objects, so repetitions are allowed. There are many ways to bracket the expression of the tensor product x1 tensor with x2 and so on tensor with xn. It is very well known that the number of ways to bracket this expression is exactly the nth Catalan number 1 divided by n plus 1 times 2n choose n. In particular, for n is equal to 3, we have two different ways to bracket the expression. The first one is when we first tensor x1 and x2, and then we tensor the outcome with x3. And the second one, when we tensor x1 with the outcome of tensoring x2 and x3. And the associator alpha of our monoidal category C provides a canonical isomorphism between these two different ways to bracket this tensor product. The problem is that if n is greater than 3, there might be more than one way to connect different parenthesizings of the tensor product of x1, x2, and so on up to xn using associators. So we can move associators in different ways to come from one parenthesizing to another parenthesizing. In particular, for n is equal to 4, we see two different ways to connect two different parenthesizings of 4 elements, and we have the pentagon axiom which establishes that these two different ways must coincide. It is a very natural question to ask what happens if n is greater than 4. And the coherence theorem answers this question. So here is the formulation of the coherence theorem, which is due to MacLane. Let x1, x2, and so on xn be objects of a monoidal category C. Let p1 and p2 be two ways to parenthesize the tensor product of these objects in the natural order, but also additionally allowing to plug in the factor I arbitrary many times at arbitrary places in p1 and p2, and these insertions might be different for p1 and p2. Let f and g be two morphisms from p1 to p2 obtained by composing tensor products of associators, unitors, identity morphisms, and their inverses. The claim of the theorem is that in this case f is equal to g. Illustration. So here is an illustration of how to understand the statement of the theorem. The theorem claims that the following diagram commutes. So we have n is equal to 3, and we have three objects x1, x2, and x3, which we parenthesize and also insert the identities in the following way. So the first way is we tensor x1 with the identity, and then we tensor outcome with the outcome of tensoring with the identity, the tensor product of x2 and x3. The second way to parenthesize is the following. So first, we tensor x1 with the tensor product of the identity and x2, and then we tensor the outcome of this with x3. So here are two different ways to start from one parenthesization and go to the other one. So we start from the first one, and first we apply the right unitor to x1 to construct x1 tensor the identity just to x1. Now we apply the right unitor to x2 tensor x3, and so we get x1 tensor product with x2 tensor x3. Now we use the associator, in fact the inverse of the associator, to get the tensor product of x1, x2 tensored with x3. And finally, we take the inverse of the left unitor for x2. And so we end up in x1 tensored with identity tensor x2, and then we tensor the outcome with x3. And here is a different way to go from the first parenthesization to the second one. We start from the first parenthesization, and we apply the inverse of the associator to move this bracket here. So we start from tensor product of x1 tensor 1 with x2 tensor x3 tensored with 1, and we end up in the tensor product of x1 tensor 1, then with x2 tensor x3, and only after that with the identity object. Now we have here the identity on the right, so we use the right unitor for the left factor to get the left factor. And now in this left factor, we have tensor product of two brackets, so we move the right bracket to the left using the inverse of the associator. And we get x1 tensor the identity, tensor x2, and then tensor x3. And now inside the first bracket, we use the associator to move the bracket from left to right, and we end up in x1 tensored identity tensor x2, and then we tensor the outcome with x3. So the theorem claims that the first composition here on the left equals the second composition here on the right. Okay, we will prove the coherence theorem using strictification theorem. By strictification theorem, there is a strict monoidal category C tilde and a monoidal equivalence phi from C to C tilde. We apply phi to the diagram which defines our maps F and G from the formulation of the theorem. Since C tilde is a strict monoidal category, the associators and unitors in C tilde are given by the identity maps, and therefore we obviously have that phi of F is equal to phi of G. But we know that phi is an equivalence, so since phi is an equivalence, it follows that F is equal to G originally. And a very nice consequence of the coherence theorem is that the bracketing in all diagrams, which involve only associator, unitors, and the identity maps, the bracketing there may be ignored. And we will later on use this quite often. Our next subject for today's lecture is the notion of a rigid monoidal category. And in order to motivate the definition related to this notion, let us recall the notion of adjoint functors and adjunction morphisms. Let A and B be two categories. Let F be a functor from A to B, and G be a functor from B to A. Recall that the pair F, G is called an adjoint pair of functors, provided that there are isomorphisms which are natural in both variables as follows. So the homomorphism space in category B from f of x to y is isomorphic to the homomorphism space in the category A from x to g of y, and such isomorphism should exist for all x and y. We also know that this condition is equivalent to existence of natural transformation epsilon from the composition of f after g to the identity functor on the category B, and the natural transformation eta from the identity functor on the category A to the composition of g after f. and such that these natural transformations satisfy the following adjunction identities. The identity natural transformation on F should be equal to the composition of the restriction of epsilon to F after F applied to eta. And also the identity natural transformation on G should be equal to the composition of G of epsilon after the restriction of eta to G. The usual terminology is that F is called the left adjoint functor of the pair, G is the right adjoint functor of the pair, the natural transformation epsilon is called the counit, and the natural transformation eta is called the unit of the adjunction. Now let us define similar notions for any monoidal category. So let's see be a monoidal category and X and Y be two objects of C. Definition: we say that the pair X, Y is an adjoint pair of objects, provided that there are morphisms, the morphism epsilon from X tensor Y to the identity, and the morphism eta from the identity to Y tensor X, such that the following two compositions are equal to the identity morphisms. So the first composition is as follows. We start with X. We use the inverse of the right uniter on X to go to X tensor the identity object. Now we use the identity on X tensored with eta, so this is our eta, to go to the tensor product of X with Y tensored with X. Now we can use the inverse of the associator to move the bracket and to end up in X tensor Y tensored with X. Now to the bracket of X tensor Y, we can apply our morphism epsilon, and then we tensor it with the identity on X, and we end up in the identity object tensored with X. And finally, we use the left uniter on X to go to X. So this big composition should be equal to the identity morphism on X. Similarly, starting from Y, applying the inverse of the left uniter, we go to the identity tensor Y. Applying eta tensor the identity on Y, we go to Y tensor X tensor Y. Applying the associator, we move the bracket and go to Y tensor X tensor Y. Now we apply the identity tensor epsilon to go to Y tensor the identity. And finally, we apply the right uniter and end up in Y. The book of Agnew uses the following terminology and notation. So X in the adjoint pair is called the left dual of Y and is denoted by Y star, where star is on the right. Y is called the right dual of X and is denoted by X star, but now star is on the left. The morphism epsilon is called the evaluation morphism and is denoted by Eve. And the morphism eta is called the coevaluation morphism and is denoted by co-Eve. There is another alternative name. Epsilon and eta are called adjunction morphisms associated to this adjoint pair. So eta is the unit of the adjunction and epsilon is the co-unit of the adjunction. Our first observation is that adjoints are unique up to isomorphism. So proposition: if exists, a left or right adjoint of an object is unique up to a unique isomorphism intertwining the adjunction morphisms. Proof: assumes that we have an object Y which has two left adjoints, X with the corresponding adjunction morphisms given by epsilon and eta, and X tilde with the corresponding adjunction morphisms given by epsilon tilde and eta tilde. Define a morphism gamma from X to X tilde as the following composition. So we start from X, we do the inverse of the right uniter to go to X tensor I. Now we apply eta tilde to I, and we end up at X tensor Y tensor X tilde. We use the associator to move the brackets, and now here to x tensor y we can apply epsilon, and we end up at identity tensor x tilde, and now we use the left unitor for x tilde to go to x tilde. So we define gamma as this composition. Similarly, we define beta from x tilde to x as the following composition. So we start from x tilde, use the right unitor to go to x tilde tensor I. Now we use eta to go to x tilde tensor y tensor x. We use the associator to move the brackets. Now we use epsilon tilde to go from x tilde tensor y to the identity. And finally, we use the left unitor to go from I tensor x to x. We claim that both compositions beta after gamma and gamma after beta are the identities. So we prove that beta after gamma is the identity. The second claim is similar. So let us consider the following diagram in which we suppress now associators and unitors in order to have a smaller diagram. So here we can use coherence theorem and say that we can do that. So here is a diagram. We start from x. So we use eta to go to x tensor y tensor x. Alternatively, we use eta tilde to go to x tensor y tensor x tilde. Now we can go from both of these, we can go to x tensor y tensor x tilde tensor y tensor x, where from x tensor y tensor x we apply identity tensor eta tilde tensor identity, while from x tensor y tensor x tilde we apply identity tensor eta. From this middle term, we can go to x tensor y tensor x by contracting here x tilde tensor y using epsilon tilde, or we can go to x tilde tensor y tensor x by contracting x tensor y to the identity. Similarly, we can go from x tensor y tensor x tilde to x tilde by contracting x tensor y to the identity. And here on the right, we go from x tensor y tensor x to x by contracting x tensor y to the identity. And in the last row, we go from x tilde to x tilde tensor y tensor x using eta, and from the last object to x using epsilon tilde tensor the identity. All squares in this diagram commute due to the fact that the maps between objects are given by certain natural transformations. The triangle here commutes because of the adjunction identity for x tilde. In particular, it follows that the whole diagram commutes, and now this means that the two outer paths are equal. The outer path left and then the bottom row, this is equal to beta after gamma by definition, because this is gamma and this is beta. And the outer path top right is equal to the identity because, so this part is the identity, and otherwise we have identity tensor eta composed with epsilon tensor identity. So this is the adjunction identity for x. And this proves our claim. So we now know that the composition of beta after gamma and gamma after beta are the identities. So in particular, it follows that the objects x and x tilde are indeed isomorphic. It remains to prove that this isomorphism intertwines the adjunction morphisms and that it is unique with such property. In order to simplify the proof, we need to make a detour and establish one very important property of monoidal categories called the interchange law, and this is a consequence of bifactoriality of the tensor product. So the theorem, which is usually called the interchange law, let F be a morphism from X to Y and G be a morphism from U to V in some monoidal category C. Then the tensor product of F and G is equal to the composition of the tensor product of F with the identity on V after the identity on X tensored with G. Also, the tensor product of F with G is equal to the composition of the identity on Y tensored with G after F tensored with the identity on U. Proof: So we recall that by the axioms of the monoidal category, the tensor product is a bifunctor from C times C to C. By the definition of the Cartesian product of two categories, in this Cartesian product, we can write the morphism f, g as the composition of f, identity on V after identity on X composition with G. And now we apply functoriality of the tensor product, which rewrites this equality into f tensor G is equal to f tensor the identity on V after identity on X tensored with G. And the other equality is proved similarly. So this is a kind of a slightly simplified version of the interchange law. More generally, one can show that the composition of the tensor product of f and g after the tensor product of h and k can be rewritten as the tensor product of the composition of f after h and the composition of g after k. Of course, in the situation where all this makes sense. So we will often use this nice property to prove commutativity of certain diagrams. Okay, let us proceed with the proof of our claim of uniqueness of the adjoint object. So we already proved that gamma and beta are pairwise inverse morphisms between x and x tilde. Let us now prove that they intertwine the respective adjunction morphisms. We consider the following diagram. So starting from x tensor y, we can insert the identity in between and use eta tilde to go to x tensor y tensor x tilde tensor y. Using the epsilon, we can contract the left factor x tensor y to the identity, so we end up in x tilde tensor y. Or using epsilon tilde, we can contract the right factor to the identity and end up at x tensor y. From x tensor y using epsilon, we can go to the identity. From x tilde tensor y, we can go to the identity using epsilon tilde. In this diagram, the left upper triangle commutes by the adjunction identity for x tilde. The left lower triangle commutes by definition, because this is the identity map. And the right quadrangle commutes by the interchange law, because it's a tensor product of epsilon and epsilon tilde. Hence, the whole diagram commutes. Now, if we compare the outer passes in this diagram, we see that epsilon is equal to the composition of epsilon tilde after, and then the top row pass is exactly gamma tensor with the identity. And all other cases can be proved similarly. So this establishes that gamma and beta indeed intertwine the respective adjunction morphisms. Finally, we need to prove uniqueness. Assume that f from x to x tilde is a morphism that intertwines the adjunctions. Then we can consider the following diagram. Again, we suppress associators, unitors, and so on. So starting from x, we can go to x tensor y tensor x using eta, and then to x using epsilon. Similarly, starting from x, we can go to x tensor y tensor x tilde using eta tilde, and then we can go to x tilde using epsilon. Starting from x tilde, we can go to x tilde tensor y tensor x tilde using eta tilde, and we can go to x tilde using epsilon tilde. So on the vertical rows, so here we have the identity, here we have the identity. The map from x to x tilde is given by f, and here it is given by f. And in the middle, we have the identity on x and y, and then f, or f, and then the identity on y, or x tilde. So now the top right and the down left squares commute by the interchange law, because it's a tensor product of f with epsilon, and here of f with eta tilde. The other two squares commute as we have assumed that our morphism f intertwines the adjunction morphism. So in this square, f intertwines eta and eta tilde. and in this square, f intertwines epsilon and epsilon tilde. So the whole diagram commutes. So if you look at the outer passes of this diagram, so here we have f times something which is equal to the identity by the adjunction axiom, and here we have again the identity using the adjunction axiom, and then f. But now if we read it down, right, down, we will get identity, and then exactly gamma, and then again the identity. And so f is equal to gamma. And this completes the proof of the uniqueness as claimed. So we have now discussed the notion of a dual object. Now we will extend it to the notion of a dual morphism. Let C be a monoidal category. Let y and y prime be two objects in C, and f a morphism from y to y primed. Assume that x is a left adjoint to y, and x tilde is a left adjoint to y prime, with the corresponding adjunction morphism epsilon eta and epsilon tilde and eta tilde respectively. So define the morphism f star on the right from x tilde to x as the following composition. We start from x tilde, apply the right unitor to get to x tilde tensor I, then we apply eta to go to x tilde tensor y tensor x. We use the associator to move the brackets, and now we apply f to go to x tilde tensor y tensor x to x tilde tensor y tilde tensor x. So now we can use epsilon tilde to contract xy tensor y tilde to the identity, and we use the left unitor to go from the identity tensor x to x. Similarly, assume that z is right adjoint to y with the adjunction morphisms epsilon and eta, and assume that z tilde is right adjoint to y tilde with the adjunction morphisms epsilon tilde and eta tilde. Define now the map f star on the left from z tilde to z as the following composition. So we start from z tilde, use the inverse of the left unitor to go to the identity tensor z tilde. Now we apply eta to go to z tensor y tensor z tilde. Now we use the associator to move the brackets. Now we apply f to y, and we go to z tensor y tilde tensor z tilde, and now we use epsilon tilde to contract the right factor to the identity. And finally, using the right unitor, we end up in z. So here is an interesting property of this construction. Proposition: let x, y be an adjoint pair of objects with the corresponding adjunction morphisms eta and epsilon. Let x tilde, y tilde be another adjoint pair with the corresponding adjunction morphisms eta tilde and epsilon tilde. Then, for any f from y to y tilde, f is equal to f right star and then left star. And similarly, for any g from x to x tilde, we have the g is equal to the right star applied to the left star of g. Proof. As usual, we prove the first claim, and the second claim is similar. Again, we suppress the associators and the unitors, and using the interchange law, we can write f right star and then left star as the following composition. So we start with y, and then on the left, we do first eta tilde and then eta, and then we end up in y tilde tensor x tilde tensor y tensor x tensor y. So now we apply f to the middle term, and we go to a similar product, but now with y tilde in the middle. And now we can use epsilon tilde to this factor and epsilon to this factor, and we end up in y tilde. Using the interchange law, we can rearrange the factors in this composition in the following way. We move epsilon, which doesn't affect this fact. So we move the epsilon term to the left, and we move eta tilde, which also doesn't affect f, to the right. And so we rewrite this product as follows. So we start from y, and we go to y using the identity tensor epsilon after eta tensor the identity. Then here in the middle we do f, and we go to y tilde, and after that we do the tilde part, so identity tensor epsilon tilde after eta tilde tensor the identity. And using the adjunction morphisms, we see that the first part here is the identity, and the second part here is again the identity. And this completes the proof. Next, let us discuss how taking the adjoint interacts with tensor product. Assume that we have two adjoint pairs in a monoidal category C. The first pair is x, y, eta, and epsilon, and the second pair is x tilde, y tilde, eta tilde, and epsilon tilde. Lemma: the pair x tilde tensor x, y tensor y tilde is an adjoint pair. We will prove this by explicitly constructing the corresponding adjunction morphisms eta hat and epsilon hat. We define eta hat as the following composition. We start from the identity. We apply eta to go to y tensor x. Now we use the inverse of the left uniter of x to go to y tensor I tensor x. Now we use eta tilde to go to y tensored with y tilde tensor x tilde and then tensor x. Next we use the associator to move the inner brackets to first x tilde tensor x, then tensor with y tilde, and then tensor with y. And finally, we use the associator to move the outer brackets to y tensor y tilde, and then tensor with x tilde tensor x. And this gives us a necessary morphism from the identity to the tensor product of these two objects. We define the adjunction morphism epsilon hat as the following composition. So now we start from the tensor product of x tilde tensor x and y tensor y tilde. We use the associator to rewrite it as x tilde tensored with x tensored with y tensor y tilde. And we use the associator once more to rewrite it as x tilde tensored with x tensor y and then tensor with y tilde. We use epsilon to construct x tensor y to the identity. So now we use the left uniter to construct the identity tensor y tilde to y tilde, and here we use epsilon tilde to go to I. And this gives us a morphism from the tensor product of our objects to the identity. And it's a nice exercise to check that these two morphisms satisfy the adjunction axioms. And this completes the proof of the lemma. Next, let us discuss composition of dual morphisms. Assume that we now have three adjoint pairs of objects, xy, x tilde y tilde, and x2 tilde y2 tilde, with the corresponding adjunction morphisms in the monoidal category C. Let f be a morphism from y to y tilde, and f tilde be a morphism from y tilde to y2 tildes. Similarly, let g be a morphism from x to x tilde, and g tilde be a morphism from x tilde to x2 tildes. Claim the left adjoint to the composition of f tilde after f equals the composition of the left adjoint to f after the left adjoint to f tilde. Similarly, the right adjoint to the composition of g tilde after g equals to the composition of the right adjoint to g after the right adjoint to g tilde. Again, we will discuss the proof of the first equality, and the second equality is similar. So suppressing the associators and the uniters, the adjoint of f tilde after f is given by the following composition. So we start from x to tilde and use eta to go to x to tilde tensor y tensor x. Now we have to apply f tilde composition with f to y. So we rewrite it in two steps. First we apply f, and we go to x to tilde tensor y tilde tensor x, and then we apply f tilde to go to x to tilde tensor y to tilde tensor x. Now we apply epsilon to tildes to contract the first two factors to the identity, and we end up in x. In turn, the composition of the adjoint of f after the adjoint of f tilde is given by the following composition. So we start from x to tildes. We use eta tilde to go to x to tilde tensor y tilde tensor x tilde. Now we use f tilde to go to x to tilde tensor y to tilde tensor x tilde. So we contract the first two factors using epsilon to tilde, so we end up in x tilde. And now we play the same game now with eta, f, and epsilon tilde. And we end up in x. So we have to compare these two compositions. And in the second composition, we see this funny factor x tilde, which is denoted in orange. So it appears here in the image of eta tilde, and then it remains, and we always have the identity map between these factors in our composition. And then we have some factors on the left of it, and then we have some factors on the right of it in each composition. And they don't interact, so we can use the interchange law to move the stuff on the left of x tilde to later on in the composition, and then to move the stuff on the right of x tilde to earlier in the composition. So this manipulation will rearrange the factors in our composition, and in particular in the middle, we will get the adjunction axiom which starts with y tilde. So this is this y tilde, and which involves this x tilde factor, which we emphasized. And that adjunction axiom will contract everything to the identity map on y tilde, thus giving us exactly the first composition. And this proves our lemma. Next, let us discuss the monoidal structure on the opposite category. Given a monoidal category C with a tensor product tensor, with the identity object I, the associator alpha, and the left unitor lambda, and the right unitor rho, we can consider the opposite category C op. So let us define the tensor product for the opposite category, x tensor op y, as y tensored x. So we change the order of the tensor product. Let us define the identity object for the opposite category as I, so the same, we keep the identity object. Let us define the opposite associator for x, y, z as the inverse of the usual associator for C, but for the object z, y, and x. And finally, let us swap left and the right unitors. And then, directly from the definitions, it is easy to see that the opposite category, together with this opposite tensor product, with the identity object which is preserved, with this new associator obtained from the previous associator, and with the new left and right unitors, this construct is a monoidal category. So given a monoidal category C, the opposite category has a natural structure of a monoidal category. And now we can finally talk about rigid monoidal categories. Definition: an object of a monoidal category is called rigid if it has both left and right adjoints or duals. A slight warning, the word rigid is very heavily overused in mathematics, especially in algebra, so maybe this terminology is not the most optimal one in this context. Definition: a monoidal category is called rigid, provided that each object in this category is rigid. And if one takes a look at all the properties for the duals, for left and right duals, which we already established, we have the following, that if we have a rigid monoidal category C, then we have two monoidal equivalences from C to C op. The first one is given by starting with an object x and going to x star on the right, taking the left dual, and for each morphism f taking the left dual of f. And the second is given by starting from x and going to the right dual. So x with a star on the left, and similarly for the morphisms. So this follows directly from the properties of taking left or right adjoint for an object which we discussed before. Because of this property, we can alternatively say that a rigid monoidal category is a category which is equipped with a monoidal equivalence between this category and the opposite category, and which is equipped with adjunction morphisms. So for each object, we have adjunction morphisms. So here's an example. Let K be a field. Consider the monoidal category of all finite-dimensional vector spaces over K. We claim that this is a rigid monoidal category. For a finite-dimensional vector space V, we define the dual space V dual as both left and right adjoint of V. So let us prove that the dual vector space is both left and right adjoint. For this, we define the co-unit of the adjunction as the evaluation map. If we have an element from the dual space and a vector in the space, we can apply the element of the dual space to a vector and we get a number. So this gives us the evaluation map. To define the unit of the adjunction, we choose a basis in our vector space. So a basis bold V given by vectors V1 and so on Vk. Then we have the dual basis V dual, which is given by the vectors V1 dual, V2 dual, and so on Vk dual in the dual vector space V. So we define the unit eta of the adjunction in the following way. So eta starts from K and goes to V tensor V dual, and the value of eta at 1 is equal to the sum I from 1 to K Vi tensor Vi dual. So we know that this map depends on the choice of the basis at the first glance, but one can show that in fact it is independent of that choice. And now let us check the adjunction axioms. Starting from a vector V, so we apply eta and we go to V tensored with this sum, the sum I from 1 to K Vi tensor Vi dual. So now we apply epsilon, we need to evaluate Vi dual at V, so we go to the sum I from 1 to K Vi times the coefficient Vi dual applied to V. And the standard property of the linear algebra tells us that this is equal to V. And this gives us our adjunction axiom. And all other adjunction axioms can be checked in the similar way. We also know that for finite-dimensional vector spaces, we have a canonical morphism between V and the double dual of V. So this completes our example. The category of finite-dimensional vector spaces over a field is a rigid monoidal category. Finally, let us discuss the interaction of monoidal functors with adjunctions. Let C and C tilde be two monoidal categories. Let F be a monoidal functor from C to C tilde with the corresponding structure given by psi and phi. Let X, Y be an adjoint pair in C with the corresponding adjunction morphisms given by eta and epsilon. So we claim that f of x, f of y is an adjoint pair in C tilde. For this, we define the corresponding adjunction morphisms eta tilde and epsilon tilde as follows. So the adjunction morphism eta tilde from the identity to f of y tensored with f of x is defined as the following composition. We start from the identity in C tilde, and we use our phi to go to f of the identity in C. So now we can use f of eta to go to f of y tensor x. And now we use the inverse of psi to go to f of y tensor f of x. This gives us a morphism from I tilde to f of y tensor f of x. Similarly, we define epsilon tilde as the following composition. We start from f of x tensor f of y. We use xi to go to f of x tensor y. Now we apply f of epsilon to go to f of I. And now we use the inverse of phi to go to the identity. And now it is easy to check that the pair f of x, f of y with the morphisms eta tilde and epsilon tilde as defined here is an adjoint pair. In other words, monoidal functors send adjoint pairs to adjoint pairs. Okay, some problems and questions at the end. Question 1, prove that the number of ways to bracket the n-fold tensor product expression is exactly 1 divided by n plus 1 times 2n choose n. Question 2, prove that I, is an adjoint pair of objects in any monoidal category C. Question 3, write down the full setup and prove with all details the general interchange law that the composition of F tensor G after H tensor K is equal to the tensor product of the composition of F after H with the composition of G after K. Question 4, check the adjunction axioms for eta hat and epsilon hat in the proof that x tensor x tilde, y tilde tensor y is an adjoint pair. Question 5, check with all details the example that the category of all finite dimensional vector spaces over a field is a rigid monoidal category. Thank you very much and see you next time.